My name is Miguel Morales. I'm the author of Grokking Deep Reinforcement Learning. I'm a software engineer. I do research in reinforcement learning at Lockheed Martin, Missiles and Fire Control, Autonomous Systems. I'm also a part-time instructional associate at Georgia Tech. I also recorded some actor critic lectures for Udacity. Very happy to have done that. Great. I'm myself a Udacity grad from multiple nano degrees, and I felt that that was kind of like going full circle and giving back to that community and company. And recently, I authored this book, Grokking Deep Reinforcement Learning, and the book is designed to help people go from a little bit of machine learning experience to here, state of the art deep reinforcement learning algorithms. Okay, now I'm not saying that the book is going to take you to state of the art research, not at all. But in part-time streaming, oh, that's great. Okay, so hopefully you like, and you let me know how it was, whether the stream had some quality or not. But yeah, so the book is designed to take people with a little bit of background in machine learning. You don't have to have much, but at least something to kind of understand what is supervised learning. I still try to go and do some refresher before getting into reinforcement learning, but the approach I take is to try to get folks going into the book and then through everything related to reinforcement learning that is not necessarily machine learning or supervised learning, what most people think of machine learning, which is really supervised learning. Most folks out there, and then little by little give you the insight as to how to use supervised learning techniques to solve reinforcement learning problems. Okay, so, and I think the book is pretty decent, does a pretty good job, I think. And it might sound silly that I'm saying that the book I wrote, right, is okay, but trust me, if I said it's because I really put a lot of effort to try to help people go from, because when I had to learn reinforcement learning, I had so many questions, and the questions were like all over the place. They were there, but you had to, watch hundreds of videos of this lecture and this other person, plus, read the books, plus read the papers, plus, and there's so much misinformation as well. So what I try to do is condense all of that stuff and put it in the same resource so that you guys can, hopefully see it from my lens, which I try to make it as clear and detailed as possible for your benefit. All right, I see. Excited for these. Answer a lot of my questions and step. Blah, blah. Awesome. Well, thank you so much, and thank you for reviewers and also MEEP supporters, early folks that purchased the book. I mean, I'm so grateful because 3 years projects is really rough. Trust me, when you have 2 little kids and 2 other jobs, it's hard. But I can tell you that whenever I went back and look at people actually supporting the book, I'm like, okay, that's what really kept me, plowing through and trying to clarify things and rewrite things and so on. So hopefully you guys have benefit from it. And, if you're still thinking about it, go ahead and grab the chapter. We're going to go over chapter 9 today. Actually, only one section of chapter 9. I'm going to show a little bit of code, but, I thought I'd rather show you how to use my notebooks than show you look how cool I am and I'm going to be coding here live. Because, first it would take me time to actually, figure out what to code live. And I'd rather kind of explain it, show you where to get the code, and then so that you can actually follow along and also, keep going. Because my point and what I hope is that people learning this thing, not just read the book and go like, oh, I'm satisfied, but that actually teaches you into go beyond that book, okay? Because this is state of the art today. That doesn't mean that it's going to be state of the art by the end of the year. Well, I don't know, with COVID, I don't know if there's going to be so many innovation or what's going to happen there, but yeah. So with that, let's get started. Let's see. So we have the comments in there. I think I can handle this. It seems kind of straightforward. we're gonna go over this book, okay, this chapter, I'm sorry, specifically. And what I want you to see is here, in the intro, and I make all these things make sense to me, at least, to me. I put them in there for a reason, okay? DQN, the way I see it, is these guys were sitting around one day and thought, how can we make the problem of reinforcement learning look like a supervised learning problem? Because we have so many different techniques ready to, you want to train a classifier to classify cats. We have that. And, there are theoretical things proven. Everything is beautiful. Everything is shiny. Everything is great. I'm not sure what that means. So for reinforcement learning, the problem is a completely different problem. And I want you to get the intuition as to what is different between reinforcement learning and, I'm going to say, supervised learning. Okay, the one thing, okay, so there are a couple of things there, but let's see. So I'm going to tell you first more intuitive, and then we're going to go into how they actually, so we can follow the book then and go more precisely as to what is that called. But if you think about how it's done with supervised learning, what you commonly have is a bunch of samples, pictures of little cats. I'm not gonna draw too much, but those are my samples. Those are a bunch of little cats in there, right? And notice something. You have all these pictures in advance, okay? You have the control of the data. So you have the control of the data. You also you know exactly what's a cat and what's not. So the rules of the games are, you're gonna tell your algorithms. Remember, we're training a supervised learning model. So you're giving supervision to the model. You're saying that's a cat, that's something else, that's not a cat, and so on. Right? That's one thing. You have control of the data. It's given in advance to you, and you can do anything you want with it. The other thing that is commonly seen in supervised learning is that the data is also diverse. So instead of having so you can imagine a picture of the same cat, and you taking pictures of the same cat all over the place, just going around in circles, taking millions of pictures of your cat, Fifi, right? No, it's not cool. You need data that is diverse, that is independent is the word, but we'll get into the words in just a second. All right, so that's one thing is really, different cats. It's not the same cat. One is red, one is green. That's my depiction of different cats. And that's enough. All right. So this is supervised learning. In reinforcement learning, it's like, you just can't do that. Reinforcement learning is trying to model online learning. You're learning from, this video stream. You can't shuffle me right now. Sorry, it's not gonna happen. I come online. The data, the stream of data comes into your sensory things, eyes, ears, and so on, online. So you don't get control of that. You get control of how you learn these data, right? You can record the video, learn later. You can go to bed later and be like, okay, so I kind of understand what he meant and things like that, and kind of replay that in your head. But you don't have control on how the data comes. And also, it's not really that diverse because, what I'm saying right now has a very particular relationship in sequence, right? So I'm saying something, I'm gonna flow the whole, teaching in a particular way. You don't get to pick I guess you get to pick if you want to switch videos, right? But other than that, you don't get to pick for this particular stream. So the data in this case, and I like to do it like this, st plus 1, and this represents states, plus 2, and so on. And then s at time t, which will be the last one. This is reinforcement learning. Reinforcement learning, this guy over here depends on this guy, right? So if you're driving a car and you're turning left, you know that what you're gonna see the next step depends on where you are at this moment, and actually something over here like a little action, right? In that case will be cap action, right? So that is all, there's a lot of correlation in there. Okay, so that's the main difference. All right, so now we're gonna switch real quick. Any questions so far? By the way, I usually welcome to the stream. Yeah, that's it, Manning. Any questions so far? Any comments so far? I'm gonna take that as we're getting the hang of it, of this. Let's see, Manning, how's it going? Okay, excellent. All right, so what I just said is basically there are actually words for this, okay? And you know, in the book we have there, this page over here, I actually, so I'm gonna go to the highlights. Basically, you can read this in your own time, but to me the highlight is this. So the data is not independent and identically distributed. That's a reality of online learning, right? When you do a supervised learning, the assumption in the data is independent, meaning that one sample, one cat is not the same cat as the other cat and the other, and so on. There are ways to go around that, but you know, sort of like the standard supervised learning does not work well if you do it that way. Okay, so independent in that sense, and also identically distributed means that you know, because you receive the data set in advance, you get to shuffle it, right? That's basically what you do every time. You get a data set, you shuffle it, and then you split it, and so on. So it's distributed identically. But you know, in reinforcement learning is not the case. In reinforcement learning, what you do today, so I cannot just teleport all of a sudden and be somewhere around the world. It just doesn't happen that way. Learning online has a distribution that is not identically distributed. Today I'm gonna experience something, and a little later I'm gonna experience something else, and then later at night, and then tomorrow, and so on. So there is some you know, sequential nature there that is very unique to online learning, and is, you know, it's very, very cool actually to have that challenge. So I would say those two things, right? So this guy, and then this guy. So that would be the first, you know, kind of issue that we're trying to solve. Remember, now let me rewind a little bit. We're trying to see what are the differences between supervised learning and reinforcement learning to try to come up with an algorithm. We're not going to come up with it, but we're going to discover it that way. That basically tries to make the reinforcement learning problem look like supervised learning to the training model. Okay, that's the whole goal that we're trying to get to right now. So the second thing is that, this is a little harder to kind of interpret, but we can go into it. Is that, let's see, where, okay, there it is. Is that in supervised learning, and I guess I can use the highlighter, right? Supervised learning, the targets are used for, the targets used for training are fixed values on your data set. You know, you have the same data set. You're going to say, this is my training data. This is my validation. This is my test. You grab batches from the shuffle data set, and the data set's not going to change. You keep doing that over and over and over and over and over and over, and then you are going to try to find that optimal, right? Well, in reinforcement learning, that's not the case, right? Because if you think about it, you know, if you want to be like a great soccer player, you start very early, you start, you know, passing the ball and so on, and you are really bad at it. You really do not see things that that a professional can see. Okay, so things are changing all the time. Things are, when you are learning, what you are using for learning is changing. Your experiences are going to change every single time step. Okay. So that is that. Let's see, what else do I have here? And okay, so yeah, so here, so we optimize this part. I think is the key here. We optimize the approximate value function, and therefore change the shape of the function. That is possibly the entire value function, which means that the targets change as well. Now, I don't know if you guys are familiar with this, but there is something called as TD versus Monte Carlo. If you don't know very much like what that, I explained in an earlier chapter, so highly recommend you go and check that out, because even though it's kind of like very, how do you say, like basic stuff, or not basic, fundamental stuff. A lot of people, are very, they just want to learn like the state of the art. But if you don't go through that process, then the state of the art, this really doesn't make much sense. But this is true for this guy over here, because there are two ways of, let's see. Should I explain this real quick? Yeah, I think we can actually explain it when it comes a little later. We're gonna have the equation, and in there I might be able to explain the difference between these two. When we get to the equation, if I don't explain the difference between TD and Monte Carlo, let me know, because I think that's important to get the distinction, to understand what it means that this section otherwise may not make much sense. That the targets change as well. What do you mean there? What are you talking about? I think I can help with that when we get to the equations. All right. So, all right. So here is a kind of, a little drawing that says, hey, so this is, you can imagine this black line being the value function, having a particular shape. And then so you get the value of the next state to calculate the value of the current state. You use that as an estimate for future, what you're going to get in the future, right? So, but you can see here, what I'm trying to say is like the red is really what's going to happen after an update. So all of a sudden, every update, you're changing the shape of your function, right? And then what's going to happen is immediately after you make that update, here is what I'm trying to the point that I'm trying to make is that point, which is the value of the next state, it's already here. It already changed. It's no longer valid. I probably shouldn't say valid, because I think that has a mathematical meaning, but I meant it's really not correct. It's no longer accurate. Okay? So that's the figure representing that. Let's see. So, okay. So again, the two problems, the targets that we're using for training are not stationary, the way that supervised learning methods have it. So supervised learning methods, remember, you have the data set, you shuffle it, and then the kind of where you're going is the same thing from the beginning to the end of training. In reinforcement learning, where you're going changes a little bit at a time. As you get better and better and better, there's a new policy. The new policy creates new data. The new data creates new estimates. The new estimates create then a new value function. The new value function creates a new policy, and so on. And that cycle repeats and repeats and repeats. Repeats, and then it's non-stationarity of the targets right there. And the second thing that we talked about, actually, which was the first thing, is that the data is not IID, identically distributed, independent and identically distributed. Okay, so how do we fix these two problems? Any ideas? Folks read already? It's like I need to get used to streaming is a little bit different, because I usually in office hours for Georgia Tech, I get to actually ask questions, and I just wait until people kind of like get back to me. And it doesn't seem that this could work nicely for this kind of stream. All right, just gonna keep going. All right, so there are actually two techniques. A couple of ways that we can make this better. Reality is online learning is just a different animal, and we should be trying to make online learning look like supervised learning. That's not a satisfying solution. But for this particular algorithm, it's a good way to. Actually, it was one of the first ones, right? 2013, 2015, two papers. One in 2013, one in 2015, and it actually started a bunch of contributions, right? I mean, can you think it? 2015, is that only 5 years ago? My goodness, so many papers have come after that, and so much like good research is out now, which is is really really good. All right, so the first thing that we're gonna talk about is, all right, so the use of target networks. Let's see. Okay. So the use of target networks. Okay, the number one addition to DQN is the use of target networks. A target network is just a copy of your network, the same network that you're training, that stays frozen for a couple of steps, so that basically the training of the online network basically uses the frozen values of the target network for many steps before that target network, the weights of that target network actually change again. Okay, so I want to be very clear with that because it's a little confusing. But here the little drawing here may help you kind of understand what I meant. All right, so you can imagine here, this is your target, right? This is in a world without a target network. The approximation would do something like that. So right, so it's gonna go here, it's gonna go here, it's gonna go here, and so on, right? But the target really doesn't stay there. In supervised learning, it does, but in reinforcement learning, the target actually is jumping because the value function gets better. I think I'm gonna have to. I need to explain the TD and Monte Carlo because otherwise you guys probably don't have a clue what I'm saying. So I realize that. All right. So let's very briefly go. I'm gonna show you the equation. We're gonna go and explain in the whiteboard. And I want people to make sure that they get the differences because it makes sense there. So the equation here for training a network is to use the reward that you experience plus this thing over here, which is basically, oh, look at that, it's fancy. This thing over here, which is basically saying, approximate, give me an estimate of what's going to happen once I arrive to the next state, and pretend that I'm gonna take the best action, the action with the maximum value, okay? And that takes me to here. Let's add one page real quick. How do you do that? Yeah, this guy. All right. So in reinforcement learning, you can imagine a grid world, okay? There's something happening in this grid world. And you always start here. Here's a +1, here's a -1. You want to, let's say that you have a very specific policy. You're always going, or so you have a very specific policy, say like this, right? These are your actions usually. If you're here, you're gonna go there. If you're here, you're gonna do this, and so on. So that's why I probably need to do more like, streaming more often, because then I could actually, talk about the different problems, and you think like, what can I do in 1 hour? And I'm like, well, it's kind of hard because I have no idea where people stand to actually help them get into the next level. But we'll give it a try. All right, so you want basically to know the value of this state. Let's say that you want to estimate that value. There are multiple ways to estimate this thing. One of them is called Monte Carlo. Monte Carlo is the kind of like more straightforward, like in my head at least. This is the way that I would do it before I knew anything about reinforcement learning. Monte Carlo is drop the agent in there, drop the guy here, and let her run the policy. Let her run it for like 1,000,000 times. It's fine. Just let the agent go around the world, experience all of the things that needs to experience, and then you can average all of that experience. You can average, right? So let's say that the reward here is 0, 0, 0, and so on. Let's say that it's actually 0.1 to make it a little bit more representative of what I'm trying to describe, and so on, right? So maybe there's something like that. You can imagine a world, right? That's Monte Carlo. Monte Carlo again says, let that policy run for a long time and we're gonna average all of the values and we're good. We only care about the value of this guy for now. We're good. The other way to do it is what is called TD, temporal difference. And that was, kind of an introduction by Rich Sutton. Well, kind of. That was an algorithm introduced by Rich Sutton. The one thing with TD is the realization that you can experience one step and predict what's going to happen from here on. And then you can immediately update your policy. You don't have to let the policy run all the way until the agent either, gets the +1 or -1. Let's say that these are terminal. Let's say that the agent terminates. So the episode ends once it reaches either this one or this one. Sorry, I guess you cannot see my hand. It's either this one or this one. Okay, that's when the agent ends the episode, right? So it's important to realize that you can also estimate the values of every single step here, this guy, and so on. And then so when you go and transition like this from here to here, you use the estimate from this second state to basically estimate the value of this guy, which is a little weird. It's like saying, okay, well, I made $1 million last year, so I know that for the rest of my life, I'm gonna make $10 million. How do you do that? Like, why would you? Well, we can do it with days, right? So I make $1 million in a day. I know that tomorrow I'm gonna make so much, and so on. It's a little contradicting or not contradicting. How do I say? Like, it's a little bit. It kind of doesn't make sense when you do it early on because your guesses are incorrect. That are not right. You have no idea. You're beginning your journey. You have no idea the true value of this guy or the true value of this guy, and so on. So the interesting thing is that in the update equation, I'm talking about that this transition over here, and I probably need to use a different color now. This transition over here actually has a signal that is real, which is a reward. And then you're going to calculate the value of that guy using that reward plus, and probably shouldn't use the discounted value right now, plus the value of that next state, S prime. And when you see Q, that's, basically the same thing. Just saying that the value and the action, given that the action is going to be like a max here. But to simplify it, let me just say like that. What I'm saying is you use the value of a next state to calculate the value of the current state. Now, this is not an equation because I need, obviously the whole target, right? But, that's what we're doing there, okay? And then so that's the difference between Monte Carlo and TD. The problem in reinforcement learning, and what I was telling you about the target network, is that when you are approximating stuff, this guy over here is going to be changing every step because this guy over here is related to this guy over here. And that is just going to spiral around like crazy, diverge. And that's why there's so many unhappy people after they try to implement some reinforcement learning algorithms, say like, reinforcement learning doesn't work, this is terrible, I hate it, whatever, okay? The point is that it's usually, there's some gotchas in there that are not easy to follow. You don't have it in your head until you actually understand the details. And so that's one of them, just to be aware, okay? Let's see, how do you change? Okay, there it is, cool. All right, so now we can go back into this. Aha, now I think you guys are gonna understand better this section. What I'm saying here is that because that value function is being trained every step, you can expect this target over here, you can expect that thing that I was drawing in there, you can expect this guy over here to be moving like this. First goes here, then goes here, then he changes here, and then he changes here, and it's just gonna keep switching back and forth. So the target is non-stationary. Bad idea. All right, so your training is going to actually try to go towards the target, right? So the training ideally would go here, then get closer and closer, and then hit the target. But it's gonna go, and then this thing just change all of a sudden here, and the training just starts flipping back and forth, it's spiraling around, divergence. Oh, okay, end of the world. How do we solve it? All right, so a target network, what it does is to, you have the two networks again, and one is going to be producing those estimates that I talk about. Okay, let's see. I need to get better at this. Where's that other thing? Ah, there it is. All right. So this guy is going to be a target network. Let's put some other color. This guy is going to be a target network. And this guy is going to be training every single time. Okay, so now your target is stationary for so many steps, right? Stationary, boom, changes, okay? And then stationary, boom, changes. And then you go like that, boom, back and forth. Back and forth, hopefully not back and forth, just, a little bit at a time, I meant. All right, so this is basically what I'm trying to describe here with the target network. So I want you to grok that just put it in your head. That's the reason why you have a target network. You want the targets to look stationary. Now, you can, I like analogies for teaching these kind of things so that you get it into an intuitive level. Imagine, climbing a mountain, right? And then you say, I want to go to the highest peak. So in reinforcement learning, what you're doing with the target network is putting, stepping stones. Like, okay, I'm gonna go to that rock first, then I'm gonna go through that path. Then I'm gonna go, even if I go down, that's fine. I go a little down, and then I go back here and so on, and then I climb it. You still have the goal that is going up to that, peak all the way in the mountain, right? But what you don't want is to try to go straight to the mountain when you're not gonna be able, it's not as easy to go straight to the mountain. In this case, that's basically what we're doing with this target network. We're actually, making the approaching of the true target or the true kind of optimum value a little bit at a time, right? We freeze the network, we solve that problem, then we update the network, we freeze it again, solve that next problem, and so on. Little by little, you accumulate all that goodness in there. All right, so let's see. What else do we have in here? I guess I, do say it here a little bit. You're sort of artificially creating several small supervised learning problems presented sequentially to the agent. That's basically what you're doing by doing that. The target network. A little problem, solve it. You're solving the big problem in the long run. Let's see, what other thing we have in here? Oh yeah, so a couple of comments there. Target network is pretty important. In practice, in problems such as the Atari games that, when this DQN algorithm was introduced, they used 10,000 steps at a time. So they froze the network for 10,000 steps, then update the weights, and then freeze it 10 more thousand steps, and so on. And I have it right here, right? So Atari games. But, for the carpal environment, which is what I use, something more simple for you guys to play around, is 10, 20 times steps at a time, okay? And you can play with that value. It actually makes a difference if you put it, too small and so on. But, the interesting thing about reinforcement learning is that so many values play part that it can get confusing to actually understand each of those hyperparameters, okay? Let's see. Yeah, so I guess this, this is the nice equation, the correct one. This over here. You can see this is basically the target, and the target uses R plus that, so on. One thing that let's see. Yeah, one kind of clarification that I wanted to make here, because it may confuse people, or it's like an interesting realization is here, allowing the online network to move consistently toward the targets before an update changes an optimization problem? Well, no, just towards the target. It's not quite the targets because what's happening here is that the R plus, gamma, max, A prime, Q, let's see, S prime, A prime, theta, and I'm just copying the function from up here. This guy over here. The target network. So you're not moving just to these guys, towards this guy. You're basically helping this signal. You're giving it time to that signal to enter your function, your online function. This is great, and I hope I don't Castro forget. I love it. Well done. That's Fede. I know this guy. That's excellent. All right. So yeah. So really what you're doing there is not just the targets. You're not going just towards the targets, but you're using the targets with a fixed thing so that the reward can actually enter your function a little bit more. So that bias, which this guy is here, is biased. That bias here is going to stay constant for a little bit as this guy, which is not biased, it's unbiased, it's just high variance, enters your, well, potentially high variance, enters your online value function. Okay. People scratching their heads. How are you doing, guys, by the way? Do we like code better? Sorry. I promised that you were going to grok this thing, so I need to go into it. Let's see. My goodness. You guys are so quiet. Am I even streaming? All right. Aha. All right. So let's do this one. Good. Good to know. All right. So, yeah. I hope so. All right. Good. All right, so we're going to go into the code. And I promise we can show you, I want to show you the code, but I feel like sometimes the code is, is the code. If you don't understand what the code says, and there's so many codes, you can get anywhere and get some examples and whatever. I don't care about that. That's not going to give you the tools to move forward, right? So I like to spend more time into kind of help you understand the pointing here, okay? All right, so the optimized model here. So there are a few things in the code actually, let's see. Should I first show you how to get the code and then go back to this? Because I don't know if you have that. Let's see. All right. Yeah, I'm gonna do that real quick, just to make sure that you guys know where to get it and so on, because I think it's important. Let's see. Translation. How do I do that? All right. I guess I need to move this microphone a little bit. Okay. And that guy is showing me. You are too bright. Okay. So how do you get the code? The code is easy to get. Go to github.com. How do you call that, tag? I don't know, username, whatever. I have every single basically place, Stack Overflow, GitHub, Twitter, whatever. This guy over here. So if you can see that, hopefully you can see that. Yes, you should be able to see it. All right, so you go there. The instructions are here. I highly recommend you get it done. I mean, it's really, really simple. You first clone the repository. You're gonna enter. Let's see. RL, Grokking Deep RL. There. So once you clone it, let's see. Once you clone it, you get in there, and then here you have the instructions, right? What you're gonna do is simple. I think this was one of the good things that I did for this book is I created a Docker image that that you can just pull. And it's gonna have everything installed for you, and I think that's actually very valuable because you don't get to have trouble with, well, I mean, you're gonna have to install Docker. That's as much as you do. Other than that, you just pull this guy over here, and that guy is even going to render the agent on the Docker container. Is gonna render the image, and then it's gonna pop it up as a GIF, as a like an animation image. Okay, so I think it's actually very valuable. So make sure you do that. Clone that, even as we are here, and then it's very simple. So Docker run it all this thing over here, and actually I think, yeah. Laha, I think it was actually who gave me, I think, the Windows. But if not, forgive me. May have not such a great memory. All right, but once you do that, and you go in there, you're gonna see that you run that command. Just follow that stuff. You have the Docker and the notebooks. Notebooks in there. You have all that. Chapter 2 to 12. There is a lot of stuff in here. It's really packed. It's good, and I just hope that you can use it, enjoy it, because there's a lot of information in there. When you open this stuff, it's gonna ask you for a password. Follow those instructions, GDRL, and then you can explore the notebooks that are working, that go match the chapters. It's very tightly developed in there. Okay. All right, so we're going to the chapter 9 notebook here. Then you just started. I don't know why I created a folder, and then a Jupyter notebook. Maybe OCD kicked in. But once you have that, the code should be pretty straightforward. You should be able to run every single cell top to bottom. What I'm going to do is I'm going to go down to the optimized model of the there. All right, DQN. So the optimize in there. Yes. All right, so from the book, I'm also going to be using the book to kind of highlight the points that are important. Target model there. So there's a target model. And then so next states is actually you're passing that into the target model, basically saying, hey, target model, give me the values of this guy, of this next states. What are the values? You detach it because these are going to be the targets. It's important that you don't pass gradients through the target model because your training is the online model. Let's say, out of curiosity, why do you decide to use PyTorch instead of TensorFlow? Really good question. I actually even threw a little kind of, how do you call that, poll on Twitter asking for advice. And I did, I evaluated TensorFlow, PyTorch, even an interesting one that I forget the name right now, but DeepMind has another library that is kind of obscure. Actually, it's not people don't know, but it's like a front end to TensorFlow. And PyTorch was much more Pythonic, I'm gonna call it, and I'm very used to. Let's see. So am I still? Yeah, it's still going. Sonnet, there you go. Sonnet is the one that, Sonnet is the one that DeepMind has that is kind of obscure, but, I was like, oh, that's exciting. I'm going to use that. But no, like I was saying before the buffer and stuff, I feel that PyTorch is more friendly if you are familiar with NumPy. And I'm familiar with NumPy. I thought, hey, there's a lot of people that are familiar with NumPy. TensorFlow before the 2.0 change, which I know they, try to kind of, I don't know exactly, I'm not, extremely informed, but they try to basically now get a little bit more like PyTorch. And, they kind of, this graph style, which I think is great for kind of production type of solutions. But for teaching, it gets in the way. When you instantiate the graph, how do you debug that thing? It's like a completely programming paradigm. At least when I was evaluating the frameworks, I know that they changed a little bit, and that's perhaps no longer true. But when I did, that seemed to be, of course, on it. Yes. That seemed to be a deal breaker to me. When you read these things, you kind of understand what's happening just by reading it. I don't memorize these things. I'm not a PyTorch guru at all. But it's kind of obvious what's happening here. There's some couple caveats there, like the max 1, like why are you passing the 1? Well, that's the axis. And then why are you getting the 0 in there? Well, because they pass back a max and then the argmax at the same time, which is a little confusing, but it's okay. Other than that, it's good. Anyways, I hope that answers that kind of PyTorch TensorFlow debate, because I think it's important. I wanted to use TensorFlow. I wanted to use TensorFlow to begin with, and I didn't even know PyTorch. I hadn't used it myself, and a lot of people recommended, no, just go PyTorch. And then I tried them both, and I was like, yeah, no doubt, PyTorch, 100%. Okay, so optimized model. So what you're gonna see here, what we're doing is we're gonna have this black box that we're gonna train to match what we're trying to do is estimate the optimal value function, all right, or action value function, if I want to be more precise. So what we're gonna do is, like you saw in that equation, and I'm gonna go back real quick to the thing. It's very, very straightforward. Tablet, let's see, transition, boom. So we're talking about that exact equation there. And I'm not gonna make this side by side because I didn't create a scene for that. So I think, it would not be smart for me to do that right now online. All right, but now we go back to the code. So what we're doing there is getting those rewards, R plus gamma times the value of the next state, the value of taking the best action, or what we think is the best action in the next state. All right. There are a couple of things there, and I'm not going to explain all of them because unfortunately we're not going to have time, but there are a couple of things there that I want you to see what's happening there. There is their bootstrapping, because I'm using the one reward and then the value of the next state. There is also off policy learning, because I'm pretending that I'm gonna take the best action, okay, to grab this guy over here. I'm saying now I'm gonna take the max action. Just calculate, give me the value of the max, and so I'm gonna calculate the value of the current state based on me assuming that when I land in the next state, I'm just gonna do the best that I can do. But in reality, in reinforcement learning, we do exploration. So that's off-policy learning there, okay? So those two things kind of have in your mind, they're happening right there in front of your eyes, okay? And then the other thing that we talked about is the target model, okay? So the target model, again, is gonna be fixed for so many steps, and is gonna be used to estimate that value of the next state. Here, boom. So the next state, the detach, then you max, then get the value, unsqueeze it, and squeeze it just puts it in the shape that is being expected, so that you can actually do the whole calculations for the entire batch at once. I'm sure that you guys can, geniuses can get much better, cleaner code, but this works fine, good, and it's good enough. All right, so now what we do is we use the max A, and by the way, the names here should be self-explanatory after you go after this a little bit, right? Max A is the max action of QSP, which is S prime, okay, of the next state. And then target QSA is the target of Q with the state and the action. So we're talking about the target basically we're using to train the current state. And then QSA is our current estimate. This is what our network, our online network, so check that out. So we're talking about the online network thinks that our values should be. And these targets are what we now can estimate our network actually should be. And then so that creates an error, right? So you know that there's a difference there, right? Awesome. That makes me happy too, the code. That QSA, target QSA, creates the error. And that is called TD error. Mostly because it's a TD target, but otherwise just we can call it the error. After that, we just train the network the regular way, the way that you would any other network. Once you have an error, you just do MSE And here I'm doing, power of 2 multiplying by 0.5, and then the mean across all those values. Then optimize, zeroing the optimizer so that there are no gradients left over from the previous step or from initializing or whatever. Then value loss backward, you do the backward pass, and then the gradients are going to stay there. And then you just do value optimizer step, and then your values get, your model improves, right? So that is that. That is the section of implementing the target network. Now, another thing I wanted to mention in this section is the interaction. A lot of people go like, well, should I use for interaction the target network, or should I use the online network? We usually just stick to the online model, okay? So it's there. Feel free to go over this. And then finally, how do we update the models, like, right? So you have the target, and then you have your online network. You need to get the target back up to speed with the online. All right. So you're gonna you have the online is more recent, right? So that's the one you're training every step, and then the target is lagging. That's the one that is fixed. And every so often, you're going to update that guy and copy the values then from the online to the target, so that the target becomes, again, the online, and then the online keeps going. So for that, what we do, this zip function is just basically grabbing two collections and putting them side by side so that you can refer to them, sequentially, one next to the other. Very simple. And then you're saying, okay, so this is the target parameters that correspond to this target. Is the online correspond to this online? And then what you're doing is grab the target, open that, copy the online data. That's it. Boom, that's it. You do that for the entire parameters, and all of a sudden your networks are identical for that particular step. You immediately collect new experiences, keep training, and so on. And, your network keeps changing and moving. Okay, let's see what else we have. Okay, so I'm gonna go back to the tablet real quick. Let's see, where am I? So transition. All right, so okay, so the next thing that we have, 7. So this is the code that we talked about. Okay, so this one is a little bit of I was very. Oh, I left the microphone. Okay, so probably need this. Okay, there. I'll be honest with you. I wanted to leave this one out of the way, kind of thing, because it's like a hand wavy type of, not solution even, is as an improvement to kind of help the non-stationarity issue. But then I thought, I read it, I heard it, I've implemented it myself, and yes, larger networks do a better job at this. But I encourage you to, prove me right or wrong, and just like play with a notebook, and I'm sure you can create a good experiment that, kind of highlights this, whether this is actually a thing or just a fantasy. But that being said, I wanted to explain it here, okay, and in the book as well. So what's going to happen is, that smaller networks are going to use the weights that it has, right, to kind of come up with relevant traits that make things similar, right? So what you're trying to do is generalize, right? When you do supervised learning, what your network is supposed to do is to look at a bunch of pictures of cats, so that when it looks at pictures of cats that's never seen before, it can actually say, that's a cat, I know it. Okay, so the same thing happens here, right? So you're training the network to do that, but the problem is when you train a very small network, chances are that you're gonna say confuse, perhaps not the right word, but bear with me. You're gonna confuse two things for the same thing. You're gonna say, oh, this, in reinforcement learning is called aliasing, right? So let me highlight there. I don't know that. So here. Yeah, so I think this is a point. Yeah, this is a good point here. Yeah, so with more powerful networks, you are able to understand the network is able to see the subtle differences that you would not otherwise. So do you use reinforcement learning at your current job? Yes, sir, I do. And it's great. It's fun, but I can't talk too much about it. But it's absolutely great, and people hate me for that, and I love people for that. So it's all good. We are all in love and peace. All right, so keep going here. All right, so with more powerful networks, you can see the subtle differences between the states, and then so it's easier for the network to look at those little differences and say, aha. So what is going to happen here is that, all right, so let's see, I see in a apparent correlation. Yeah. So the hope, okay, by this using larger networks is that two states that are correlated, because the problem is that the two states that are correlated look like the same and they change, and then everything changes basically, right? So sequentially things continue to change as you improve that. The hope is that a larger network would not too quickly overfit. Oh, why did I use that word? But anyway, overfit to that particular sample, and it will be able to actually see the differences in the samples in a better way, more robust. Okay, so try to read this. No, here. Try to read this paragraph over here. So yeah, by aliasing here, I mean that the fact that the states look alike, and there are, I think later in the book, actually chapter I think it's 11, I actually go into some detail as to what do I mean by aliasing, and I even give a little example that's kind of cute and so on. Let's see. All right, so boil it down. Ways to mitigate the fact that targets in reinforcement learning are not stationary. Yeah, so here's like a little summary. When you gotta enjoy this kind of like cute icons and stuff. But hopefully you read the text inside, and this is basically a summary of this few minutes that we've been going through this. Wow, 1 hour. All right, we're gonna keep going for a little bit at least, because I wanted to finish DQN. I would not just stop Cole. Let's see. Okay. Okay, we kind of rewind all the way to the beginning. And remember, we're talking about DQN, an algorithm that is trying to make the supervised learning problem seem more like, the reinforcement learning problem seem more like the supervised learning problem, so that the methods, the deep neural networks can be trained more easily. And we talked about the two things: one, the stationarity of the targets, which we solve by using the target networks. And the second thing is that the data is not IID, independent and identically distributed. Okay, so you remember when the pictures of the cat we have in there, when we get a data set, usually we just grab it. First of all, it's also so it's, you have the same data set. I don't want to reuse words that don't fit in there or that I shouldn't. You have the data set there. You shuffle it, and you collect samples, and you use those samples to train the network. In online learning, the way that we can handle this, and here I'm talking about NFQ, which is the algorithm that I talked about in the previous chapter, but I think we confuse things a little bit. So let me see where I can fast forward. So the experience distributor. So okay, here we just go back to the solution. The solution to making the data look more IID, independent and identically distributed, is to use what is called a replay buffer or a replay memory. So the process of experience replay consists of a data structure which is often referred to as the replay buffer or a replay memory, or very similar definitions, but commonly used. This replay buffer, what it's going to do is going to hold experience samples for several steps. much more than is probably not relevant. Here. And allowing the sampling of mini batches from a broad set of past experiences. So this is the key here. So having a replay buffer, so I'm continuing to read, has two critical things. First, the training process can use a more diverse mini batch for performing updates. So remember now, so if we have a huge replay buffer and we're collecting samples, let's say we have 1 million samples in there, chances are that there are multiple policies that have been adding samples in there for multiple conditions, right? So the experience set, the entire thing is more like a data set how you would get it, a bunch of ImageNet or whatever. You get all the pictures at once of all of the things that the agent is going to ever see, right? So you have the whole set. It's much easier for you to, for your agent to use that and learn from that broad set. And then the second, well, this is more related. The second thing here is actually related to NFQ, which I didn't explain, so I'm not gonna give that detail. But let's see. Otherwise, how if your replay buffer uses slow. Okay, we're gonna get into more detail, but yeah, a little here, history bit. Can you believe it that this experience replay is actually introduced in a 1992 paper? It's kind of crazy, when you think about it. Deep reinforcement learning, yeah. If we don't call it deep, we don't pay attention. But in reality, many of these things are actually, things that, have been researched and going on and so on for quite some time, which is, kind of cool. Let's see. All right, so my cheat sheet. Using a real, I need to fast forward a little bit. All right, so using a replay buffer as we get the impression. So yeah, that's the key right there. So, well, that's the key right there. Okay, so I wanted to see it here in this picture. So this is the DQN with a replay buffer. Notice that I'm not saying and a target network because that would make a mess in the whole drawing. But it's only like this is how it would be with the replay buffer. What happens here? So I'm gonna call this kind of like the interaction starts here. The agent selects an action. Well, actually the proper way to start this whole thing is this way with an observation. So the agent is able to observe the world, right? Then takes an action and collects that experience of taking an action and then have another reward. That experience actually is going to come into the replay buffer, so it's going to get stored here, right? Let's see, and then you use this one and a new one, right, with the action to collect it and put it here, and then you use a new one, and you get the point what I'm doing here. You use this one and a new one, and then you put it here, right? Well, actually, in reality, you put all these sequentially, but you get my point. So they actually put one next to the other. If you're doing sequentially, you're just adding it sequentially. What you do though, is to sample it uniformly at random. And this kind of gets a lot of people because when I implemented this myself too, one of my first ideas, when I read the paper and I was like, they're so silly. You can just sample the highest reward so that the agent learns the highest reward. That's the way to do it. Let's do it that way. And yeah, it didn't work, and it doesn't work. So I actually explain a little bit more, in the what is it? Actually, the following chapter, prioritize experience replay. But I give some intuition, but for now, it's just like the way you want to sample it in this case is at random, uniformly at random. Just sample from the entire buffer at once, right? You create a little mini batch. Where is it? There. You create a little mini batch. A mini batch, and then you use that to train your function, right? And then from those Q values, you pass it through an exploration strategy, usually, epsilon greedy and so on. Yeah, super excited too. All right, epsilon greedy strategy and so on, and then select the action and keep going like that. Boom, boom, boom. That's really what the replay buffer is. It's not really anything out of this world, but I want you to see it, to visualize, to kind of capture what the replay buffer is really doing for us, right? So what you're doing is you have this data coming sequentially online, all this stream of data, and you put it in the buffer. And then one day, one night, you all of a sudden just lay down in your bed and start thinking about what happened yesterday and what happened the day before and so on. And you use that thing and you pass it through your brain and you go like, yeah, I should have done it this way. I should have done that. I should do this way and so on, blah, 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 blah. That's really the replay buffer. It's like a whole, collection of memories, right? That you can use for training in a way that the data now looks that is independent because, in reality, these guys are kind of correlated, but the guy over here and the another guy over here and so on are not. So once you pull those guys, those are independent for the most part, and identically distributed, because if it's large enough, the buffer is large enough, then you're gonna have like basically experiences since like, oh, when I was a kid, I did this and this happened and so on, but also when I was teenager, this and this happened, and for the entire history of the agent, right? Good or better. That's what you do. All right, so cool. One little comment here before we flip to the notebook and then wrap it up for tonight is that the implementation that is in my notebook is for first of all not compatible with images. I let you do that, and I think it's actually a good exercise. But also, if your replay buffer needs to be very, very large, you're gonna need a different data structure. Okay, and there are ways to do that, but I just didn't want to pollute the teaching of the components with implementation details to make to get better performance out of the components. All right, so the better performance out of the components, I recommend you go to OpenAI. They have an implementation of replay buffer. Before that, I highly encourage you to try to implement it yourself, or try to implement a very efficient version yourself. Then look at what they're using. They're using a very specific data structure that helps you insert data and so on. I want you to keep in your head, one thing is like for things such as Atari, for instance, you have a stack of 4 most recent images. Usually those are 84 by 84. So 84 by 84 by 4, that is a lot of information in there for one. So if you keep in Atari, they usually recommend 1 million. So here, and if you don't do 1 million, sometimes it doesn't work depending on the game, but it doesn't work really well. That's a lot of data. Okay, so your computer doesn't have that capacity. So there are ways, or even if it does, it just makes no sense to use it. I don't think it has it. It has that capacity. One thing you can do is this things are correlated, so you can create like more efficient data structures that instead of actually having the data, have the data that is that different experience samples have, and so on. There are many tricks that you can implement there to make all of this better. But just a heads up that it is another kind of another chapter to go into the details. I don't like when people just plop code and say like, yeah, go ahead and do it. So just to give you that heads up. All right, so let's see. I think I'm wrapping up soon. Replay buffer grading update. Okay, so throughout the book I did this because I'm not a math expert, but I like people to kind of get familiar with it. Because I feel that is so important for a field like reinforcement learning, deep reinforcement learning, that you need to kind of open up to the equations and kind of read them, be able to understand it. So what I try to do is kind of write the equation the best way I thought for that particular case, and then kind of give you a little bit of comments on each of the equations and the things that I want you to see, right? So the main thing to see here in this one, for instance, is, on the previous one, we had the difference between the target, let's see here. Yeah. So we have the difference between these two. The main difference is this. This represents the neural network weights. Okay, here you can see that it has an eye. The eye basically is following the every time step type of thing. And actually time step, I mean iteration. So every time that you improve the network, which in this particular algorithm, I and T, which is a time, or actually, yeah, and T would be basically the same in terms of, you know, the entire set of episodes. Maybe not confusing too much in there. But then this one is the change in there. That, you know, theta with a little sign up there is basically saying that is the frozen network. So that's the little thing I want you to see there. That guy over there is using a network that is static for some time. That's that kind of like what they use. Now here I'm using online experiences, right, to make it a little confusing. But here I try to clarify it when the full equation comes up. And then here from that same function, equation, using the target weights and the online experiences, now I continue to use that, but now I use the replay buffer. In the replay buffer, basically the same thing. D, I mean, it's very simple. D is the data set. U is the how you sample this thing uniformly at random. That function you sample, this squiggle thing is sampling, and then you get the samples that you're gonna use for training this thing. Okay, so it's very simple in there, and this is the last part. A simple replay buffer. There you go. All right, so boil it down, and here I kind of explain it. You know, very technique. I'm sorry. The technique is very simple. It's been around for decades. As your agent collects experience tuple, blah, online. This is what's called the experience tuple. Usually, you know, here you actually have also a D, but I don't want to get into the details for that. Online, you insert into the data structure, commonly referred to as a replay buffer, D, and such as D has all that experience, and M is the size of the replay buffer, and the value is usually between 10,000 on a million, depending on the problem, of course. And then we train the agent on the minute batches sample uniformly at random, usually uniformly at random, from the buffer. So that each of the experience samples has the same probability, equal probability of being selected. Okay, and now we can switch to the code to look at that real quick. And then we wrap up for today. I don't know whose brave souls that stay with me all this time, but thanks for that. Let's see. All right, so screen transition. There you go. And I need to move this guy, I suppose. Okay. All right, so again, the replay buffer, not the best implementation in the world, but it should be very straightforward. My purpose was to make it easy for you to read, to understand, and to go like, aha, I know what he's doing here. Not for me to say, oh, look at my code, it's so cute. All right, so the replay buffer right there is very simple. I'm creating an empty numpy array. I don't want to complicate things too much. An empty numpy array that has a max size preset, and I do it empty and not a pen and stuff like that to make it a little faster. Could just collect that memory, put it in there, and then just use the memory from the get-go, but it consumes more memory, okay? So just have that in mind. Yeah, so you have that in there. Let's see what else. I have notes in here. Okay, so that's fine. So some variables there. Here, max size is, you know, the maximum size that you want the buffer to be, but the buffer is obviously at the beginning when it's being filled, has so many samples, and then continues, boom, 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 until it hits that max, and then you keep the max so it doesn't go beyond. What we do normally is evict the old ones, so the old samples just get out just one at a time, no, you know, special way, just fill up that buffer and then sample uniformly around them. This is a simple way. Yeah, so in the, let's see. So the store function, I'm getting a sample variable, which basically has the different things. In this case, I'm going to have a state, an action, reward. P is prime, stat prime. So P storage, and then D, which is going to be the done, which we use for training. We insert them in the buffer. What I'm doing is this self IDX is actually keeping the index where we need to actually put that value. The index is gonna go up, 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 and then it's gonna go. Look at this. Actually, yeah, max size. So I'm actually going back and overriding the whole thing. Oh, that makes sense. Yeah. So overriding. So here's the buffer. Let's see. Why am I recording? Yeah. Here's the buffer. I go boom, 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 and then go back to the beginning. Boom, 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 boom. So every single sample stays like that. Oh, where to the back there. It's good. It's good. It's fun. Yeah. No, I'm still working too. So no worries, man. It's a lot of fun though. Then yeah, there it is. So that's okay. So that's the ID. The size. What we're gonna do is we're gonna increase the size until it hits the max. And once at the max, you pick the min between the max and the size, and just basically gonna keep the max size. So it's it basically size is not gonna grow there. The only thing I'm doing that for is so that I can actually ask the question like, what's the size of my thing right now, and it's not the ID, because the ID, remember, it just goes back to the bottom. So there are many ways that you can implement this thing. This is the way that I thought it was the easiest to read. So you can go top to bottom and read the things very simply. And then so the sample function is basically, like I said, it's a random choice. The probabilities are going to be basically, random choice is going to be uniformly. If you don't pass a P, I suppose, I'm sure, because I implemented this. Let's see, size, batch, and replace. And then so without replacement, get the IDs, then index the memories. So you're going to get the different samples and the different memory buffers for each one. VStack a vertical stack, so that you can actually now do the equations for the entire mini batch, and then pass that experience back to the training process. And that's it. And that's your replay buffer for you. Once we run this thing, and it should be really, really nice to run. So yeah, so you can see they're running. To me it's kind of funny because, when you read some people having trouble with the carpal, and you go like, no, you should not have trouble with the carpal, and then they go like, yeah, I have trouble with carpal because reinforcement learning is really hard to train, and it's because of this, and you're like, no, it is not. You should be able to train carpal without a problem. So I say just go ahead and implement, like use my notebook, and you'll see that it shouldn't be that terribly hard to train, and not the 200 step carpal, the 500 step. I highly recommend you do that. And yeah, after you finalize that training, which shouldn't take a couple minutes, you basically can render the DQN agent progression. In this case, episode 0. This is when it's training, right? So you can see here it's tipping over pretty quickly, right? And then the episode 62 is actually learning to kind of stay a little bit, but goes off the screen, which is also a terminal state. And then episode 125 gets a little bit better. 188 gets pretty good, and then 255 is like, this is a piece of cake, I'm good. And then I'm also demoing the fully trained agent for a couple of times, so you can see the fully trained agent, how it is doing. You can see it's just it's bored. This is easy. So my challenge to you is go ahead and use this to train a different environment. You can use either the same notebooks. You will have to perhaps use some other environment that is already installed in that Docker container, or just use the algorithm and train it in a separate notebook, but share it with me, because I think that to me, one thing in learning, the best thing that I can do for you, and I transition to that camera. All right, so the best thing that I can do for you is really motivate you and kind of explain you a little bit at a time. But the learning really happens when you take over, when you say, okay, I'm gonna try it now myself. So I encourage you to try it out, to try something out, to do something full. Doesn't matter. Share it. I share it with the world as well. I think that's really what we need more of in this world. So yeah, I don't know if there are any questions. I see that we only have what do we have? 16 left. So people are still hanging in there. That's good. Any comments, guys, before I say goodbye and wrap it up? Joseph, it's good, man. It's awesome. No, I hope you enjoy the book. And thank you for supporting. It's great. Fede, awesome. More, please. Yeah, I'll think about that. I have to go from like 0 to to explain a little bit more, because I think there's so much good information here that we should, get people also to get excited about it. Okay. Well, with that then, I guess I'll see you around. So, first of all, and I'm sorry. First of all, I want to repeat one thing: is thank you so much for your support. It meant the world to me. And the book is about to get released. So you're gonna love it. I hope so. So you're gonna like it. Let me know if you do, and let me know if you don't too, because I learned from that. Just like any other agent. All right, guys, take care. Stay safe too.